Hey guys, Miss Marustic here, and in this video I'm going to talk to y'all about Le Chatelier's principle. Now, I'll be honest with y'all, I took Spanish in high school. I did not take French, so I know I'm giving this guy's name the Texas twang. So apologies to those of y'all that took French and can say his name correctly, but I say it Le Chatelier's principle. Le Chatelier's principle is all about applying a stress to an equilibrium system. Now, as a reminder about equilibrium, equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. However, at equilibrium, your amounts of reactants and products don't have to be equal. In fact, they end up being this lovely ratio right here, our equilibrium expression. Our Kc is what we can use to express what that ratio of reactants to products would be at equilibrium. So, when we stress out a system, what we're doing is we're throwing it off of this balance. Think of it as being kind of like a seesaw. A seesaw has a particular balance to it, and if I add or remove things from either side of the seesaw, that throws the seesaw's balance off. And so then I've got to kind of shift some things around on the seesaw in order to get my balance back. And that's exactly what's going to happen here. We're going to do something to stress out, to shift our equilibrium off of being on our balance, and then we're going to have to, in response, shift things back around in order to get our balance back. So to kind of see a numerical problem with this in action, we're given here a lovely reaction where we see a double arrow being used, which means it's reversible and could reach equilibrium. And they give us some starting concentrations here of A, B, and C. And so what I'm going to do is I'm going to set up a Kc expression for this. So what that would mean is my Kc would be my product, which is C, raised to its coefficient, which is just 1, over my reactants, which are A and B. Again, both of those raised to a power of 1 because they both have a coefficient of 1. And if I actually plug in my numbers to this, we end up with 5.0 over 1.0 and 2.0, which gives us a value of 2.5. So that 2.5 is my Kc value. It is my ratio of reactants to products at equilibrium when I've reached my happy balance. And what we're going to do is we're going to do something to the system to throw off that balance. So you notice here on part B, it says, hey, we're going to add in some extra B. So instead of B being 2.0, B is now going to become 4.0. And what I'm going to do first is I'm actually going to see what that does to my ratio. Now, instead of calling it a Kc this time, I'm going to actually call it a Qc, because now I'm not at equilibrium anymore. But just as a reminder, Qc has the exact same equation as Kc does. So I'm going to plug in my numbers again, except this time, instead of B being 2.0, now my B is going to become 4.0. And when I plug in those numbers, that gets us a value of 1.25. So what that means is that as of right now, my Q has become smaller than my K. My Q, the ratio that I'm at, is smaller than the ratio that I want of 2.5. So in order to get equilibrium back, I'm going to need to increase my Q so that it becomes equal to K again. And in order to do that, if I think about my equation here, to raise the value of Q, I'm going to need to increase this products, this numerator. And as a result of increasing the products, what that means is that my reactants are going to decrease. So we're going to end up increasing products and decreasing reactants. So if I think about that now in our infamous Rice table here, what that would mean is that both A and B are going to go down by some value of X. And again, it's a 1-to-1 ratio here, so I don't have to put 2x or 3x or anything like that. C is going to go up by X. And so at equilibrium, I would have 1.0 minus X, 4.0 minus X, and 5.0 plus X. Now, if I took these, plugged them back into the Kc, I could then figure out what X specifically is and know exactly how much these concentrations are changing by. Unfortunately, this is one that if you plugged everything in, you'd end up with like an X kind of squared situation on the bottom and only X raised to the first in the numerator, and so that would require you to use quadratic equation to solve. As a reminder, College Board will not ask you to solve quadratic equation on your AP test, so you don't have to stress. So what they've done on this problem actually is they have given us the possible values for X. Remember, quadratic equation will give you two answers, and only one of them is going to be logical here. You notice after solving it, they figured out that it's either 0.4 or 5.0. And if I think about those two answers, if I used 5, I'd have 1 minus 5, so I'd have a -4 concentration, which obviously is not feasible. So 0.4 is going to be kind of our winner chicken dinner here, because that would ensure that we don't end up with a negative concentration. So what that means is that if I use that 0.4, I can figure out that, hey, at equilibrium now, what would happen is that I'd have 1.0 minus the 0.4, so I'd have 0.6 molarity for A. I would have B being 4.0 minus the 0.4, so that would be 3.6 molarity. And then C would be 5.0 plus the 0.4, so that'd be 5.4 molarity. And I'm going to let you in on a little secret. If you take these and plug them back into your equilibrium expression, so 5.4 over the 0.6 and the 3.6. Spoiler alert, that ratio ends up being 2.5. So we ended up reestablishing that same ratio that we had to begin with. So let me kind of walk us through here for just a minute, kind of what we've done from a little bit of a different perspective, from the idea of having a seesaw. I had a balance of 2.5 to start off with. What we then did is we added in some reactant. And so that made that side of the reaction too heavy. And so in order to fix my reaction, I took some of those reactants and shifted them over to the product side. And what that did is that ended up getting back the balance that we had originally. Okay, now this is all using math and numbers. We can also see this same process done graphically. And so this is kind of a common question or a common question prompt you might see on the AP test. So if you look at the next page, you notice they're showing us graphically the exact same process that happened on the previous page. I'm starting off with concentrations of A, B, and C, the 1, the 2, and the 5. I then, at that point, had my Q equaling my K. At that point, those two were equal. Remember, Q is a ratio that can be taken at any point. K is the ratio at equilibrium. So since that was at equilibrium, the two were equal to each other. So then what we did is we added in some B. So there's where we added in that B, and we can see, oh, that's thrown off our balance now. So now all of a sudden, here is where I've got too many reactants, and so my Q, as we said just a little bit ago, ends up being smaller than my K at this point. So in order to get the balance back, you notice they've shifted around some of these amounts. My two reactants lost, my product gained, until here equilibrium was reestablished. We see those curves flatten out again for concentrations. So again, the Q has re-equaled the K at equilibrium. I do want to point out that if you notice here, it doesn't look like these are spaced the same as they were originally, and they're not. However, if I do actually go and plug them into my Kc expression, if I actually go plug in those concentrations into this equation, we will see that those ratios here are equal to the ratios at the end, even though spacing-wise they don't look like they would be. So this is just one example of shifting equilibrium. I could increase a reactant. I could increase a product, I could decrease things. So what we're going to do next is we're going to talk about all of the various things that I could do to shift us off of being on equilibrium, and then how we would need to shift things around to get back to equilibrium. So the first thing that could stress out our equilibrium, as we just saw, was changing concentrations. Now this first one here is the scenario that we've kind of already gone through here. It says, hey, if we add more reactants to the mixture, what happens is that the Q ends up being smaller than my K. And so we ended up having to take some of those reactants and shift them toward the products in order to increase Q to be back equal to K. So again, I get us off of the balance, and I got to shift things around to get that balance back. On the flip side, if you add more products to the mixture, what happens there is, if I think about my lovely equation, if I add more products, now the numerator is too big, and so now my Q ends up bigger than my K value. And so in order to get Q back down, I'm going to need to take some of those products and shift them over to the reactants. Now, I kind of want to point something out here. Notice on both of these scenarios, I'm adding to one side, but then shifting to the other. So for example, here I added products, but that actually shifted me to the reactant side. We're going to make a summary statement here in just a moment where we kind of use that idea to our advantage to help us remember what's happening. All right, so on the next one here, it says, hey, if you remove reactants from the mixture, so if I remove reactants, that gets this too small, and now the products kind of is too big in comparison. What that means here is that my Q is too big in comparison to K, and so to get Q back down, I would need to shift towards the reactant side. Okay. If you remove products, if I make this numerator too small, again, that would mean that my Q value is too small in comparison to K. So to get Q back up to K, again, I would need to make the products go up and reactants go down, meaning I'm shifting toward the products. Now notice on these two situations, on things that I've removed, I'm actually shifting to the same side I've removed them from. So to give us kind of a summary statement here of what's happening, we shift away from what we add, and we shift towards what we, I don't know why I underline that, towards what we remove to replace it. Okay, so that's why I don't know why I underlined that. Away from what we add and towards what we remove to replace it. So again, thinking like our seesaw scenario. If I add to a side, so I make that side too heavy, then what that means is I need to shift things away from that. So if that side's too heavy, I need to shift things over to the other side of the seesaw in order to get it balanced again. If I remove things from a seesaw side, that makes that side too light. So like if I remove some from this side, that makes it too light. And so in order to weigh it back down, I need to shift things from this side over to that side in order to get it back balanced. So again, I'm shifting towards what we remove in order to replace it. So that's kind of a little trick you can use to help you remember how to change around those concentrations to reestablish our equilibrium. Now, there's one other thing that's mentioned on here. Notice that it says the Kc value does not change in any of those scenarios as long as your temperature is constant. So again, in all of these situations, we're not changing the value of K. We're not changing the ratio I'm trying to get to. All I'm doing is I'm changing my scenario off of being at equilibrium and then trying to get that ratio back. So all of these do not change the K value. They change Q, which then we need to get back to the K. Now, temperature, if I change that, it actually does change the K value, and we'll talk about that scenario here in just a minute. The next one I want to talk about is changing volume, which results in changes in pressure. Now, this specific scenario only impacts gases, so we have to be really careful here. We're always looking for reactions that involve gases, and I know this reaction doesn't say so, but technically all of these substances in this scenario were gases, so if you want to go and add that in. To think about this one, I actually kind of use the situation of having a party. If I'm having a party and I'm having it in a really big space, like a gymnasium or a cafeteria, then I'm cool with having a lot of people at my party. Actually, I want more people at my party than I would if I had it in a smaller space, because otherwise the party's going to look dead if I don't have a lot of people there. But then if I take my space and I decrease it, so all of a sudden I can't have my party in a gym, maybe I have to have it in a teeny tiny little room. I don't want to have a lot of people at my party anymore because everybody's going to be really squished. Okay. It's like being in an elevator. If I'm in an elevator, I don't want to be in there with a lot of people. I'd rather be in there with as few people as possible. So I'm not like scrunched up in the corner, like having everybody squished around me with their luggage or whatever at a hotel. If you've ever been in a hotel where you've had to ride down a lot of flights of stairs, you know what I'm talking about. So it's more ideal to have less people in that smaller space. Gases are the same exact way. They don't want to feel squished unless they absolutely have to. So with that said, instead of thinking about the number of people here, we're going to instead be thinking about the number of moles of gas. For example, in this situation, if I look at the reactant side, I have a grand total of 1 plus 3. So I have 4 moles of gas on the reactant side, and on the product side, we only have 2 moles of gas. And so that's going to impact us in kind of thinking about this situation here in just a minute. So here's the deal. If you increase the pressure, and thinking back to Boyle's law, we would increase the pressure, we would increase the number of collisions. If we decrease, so I'm going to put decreasing the volume of our container, the reaction will shift to the side of the equation that has fewer number of moles of gas. Again, if I'm in a smaller space, I want less people at my party. And if I notice here, the one where it says, hey, increasing pressure, look at that volume, they made it smaller. Notice how much more NH3 I have in this one in comparison to where I started. So we've shifted to that side that has less number of moles of gas. It only had 2 versus the 4. On the flip side here, it says, hey, if I decrease the pressure on the container, and I would do that again by increasing the volume, thinking back to Boyle's law, gas laws, the reaction will shift to the side of the equation that has greater number of moles of gas. So again, if I'm going to have a party where I have a much bigger space, I want more people at my party. So if I notice on here, this one where they've decreased pressure, I notice how much bigger that volume is. And if I look here, look how few NH3s are in this container. Almost everything is the N2 and H2. So again, I've shifted to the side that has more moles of gas. Now there is a mathematical reason why this works. It has to do with concentration. So we'll talk about that here in a minute. But first I want to talk about a common question that I see on AP multiple choice style questions. And they may ask you like, hey, which of these equations would actually get affected by changing pressure and volumes? Which one, would actually get stressed by these particular changes and have to shift its equilibrium? And you're looking for a couple things on something like this. First off, you're looking for a reaction that actually has gases in it. So first off, if I look through these, I'm notice, hey, this last one, this is a salt dissociation. That doesn't even have gases in it. So there is no way that that could remotely be the answer here. So then between the other two, I'm looking for a reaction where the number of moles of gas actually change. Okay, if the number of moles don't change from side to side, then that means increasing and decreasing the size of that container isn't going to cause any shift. If I have 10 people at my party, whether it's a big space or a small space, then it doesn't really matter if I increase or decrease that space. So if I look through these, this first one here, I have 1 plus 1, so that's 2 moles of gas on this reactant side. And I also have 2 moles of gas on the product side. So for this one, even though I have gases, changing the pressure and volume won't actually change my equilibrium up. Now on this one, I know we see that solid there, but as a reminder, when I'm setting up these equations, solids and pure liquids don't get included in equilibrium expressions, and so that wouldn't have even been in my equation anyways once I set up my equilibrium expression. So if I look at just the gases here, I notice I have 1 mole of gas on the reactant side and 2 moles of gas on the product side. So this one actually does have a different number of moles of gas on either side. So this one would have been our winner chicken dinner there. That's the one that would have been affected by pressure volume differences. So again, if you're ever asked a question like this, you're looking for one that actually has gases in it and one where the number of moles of gas are not equal on either side. All right, so now let's talk about the mathematical reason why changing pressure works. And it actually has to do with the tie that changing pressure has to concentrations, to molarity. So if you notice on here, they give us a lovely reaction here that has a reversible arrow, so that means it could reach equilibrium. And they've given us a Kc value. So this is the ratio that would be ideal for this particular reaction at 100 degrees Celsius. And then it says, hey, we have these beginning concentrations at equilibrium, but then it says the volume of the container is then reduced by half. And the first part of this question asks, what would happen to the concentrations of each of the substances if the volume of the container was cut in half? This actually goes back to something we talked about in solutions. If you remember, we have a lovely equation called Vim-Vim. Vim-Vim is when I change the volume up, what impact that would have on the molarity. And so if here, volume of the container was cut in half. If I lower the volume, because the way that this equation is, because it's a multiplied thing, that would cause the molarity to go up if it's still equal to this other side. So what that means is that if the volume of the container was cut in half, the molarity is going to increase in a proportionate amount. So if I half the one thing, then that means the molarity would double. So that means my 2.0 here would end up becoming 4.0 molarity, and my 0.65 here would end up becoming 1.3 molarity. Okay, so then on this next part here, it wants us to calculate the new value of Q once the volume of the container was cut in half. So I'm going to set up my equilibrium expression, except I'm going to do it with QC since we're not at equilibrium yet for this one. So again, my product is the NO2, except it gets squared over my reactant of N2O4 raised to the first. So again, I'm using those coefficients here to raise my exponents. So plugging in my new values here, the NO2 is now 1.3, but that's going to get squared over the N2O4, which is 4.0. And when I plug in all those numbers, that gets me a value of 0.42. So what that means is that my original ratio that I want is 0.21, but now my ratio has jumped up to 0.42. So my Q is bigger than my K. And as we know, that can't happen. So in order to get Q being too big, in order to decrease Q, what that means is that we are going to have to decrease my products and increase my reactants, right? So remember, to get that Q to go back down, I'm going to need to make that denominator bigger and the numerator smaller. So what that means is that it's asking me in which direction would the reaction shift. We are shifting to the reactants to fix this. Okay, now, next question asks, did the reaction shift toward the side of the equation with a greater or lesser number of moles? Well, we shifted to the reactants. Let's look back up here. The reactants had 1 mole. The products had 2 moles. We are shifting to the side with lesser number of moles, which, if we think about it, should make sense because we said, hey, if I cut our container in half, if I make my container smaller, I don't want as many people at my party, and so therefore I should be shifting to the side with lesser number of moles, which actually ended up working out. Now the reason why this works actually has to do with these coefficients here. When I change the container, that changes both the individual molarities the same. However, because this numerator was squared where the denominator wasn't, because of the number of moles of gas, that ends up affecting our ratio in a particular way. So the reason why this works actually has to do with the coefficients. Surprise, surprise. Now, there's one more question down here that I want to talk about because this is one that College Board likes to trick us with. They like to be mean and add tricky things. It says, hey, would adding an inert gas like argon cause any change in QC? Well, inert gas means that our gas does not react. Thinking group 18, noble gases, those don't react. And so it asks, hey, would it cause any change in my ratio? Well, If I think about it, if adding argon doesn't react either of these, then what that means is that these concentrations would remain exactly the same. And since the argon is not included in the reaction, it wouldn't have gotten included in the QC calculation. So therefore, adding the inert gas would cause no stress. To the reaction. Meaning there would be no shifting of equilibrium that has to occur with this. Now, there is one change though that this would cause. My total pressure in the container would increase, okay? Adding another gas in would cause more pressure to build up. However, because the container hasn't changed size in this situation, the original gases, the N2O4 and the NO2, their individual pressure doesn't change. The total pressure changes, but not the individual one. And if the individual one doesn't change, then I'm not changing concentrations. To kind of think about this from another perspective. If I have a container here, okay, and let's say it's a 1 liter container, and let's say I have 3 moles of some gas in there, which I'll represent by 3 molecules. 3 moles per liter would be 3 molar. I could still add another gas in here, but if I'm talking about the concentration of that pink molecule, it's still 3 moles per liter. I haven't changed the concentration of it, even though I've added an additional gas in. So just be very careful with that kind of question. It's kind of a tricky one. It doesn't cause a stress. The total pressure in the container would increase, but it does not change individual pressures or molarities. Okay, so those individual ones don't get altered. All right, one more thing we can do to shift equilibrium, which is on the next page, and that is changing heat/temperature. Now we have to be careful on this one because we get a different effect depending on if our reaction is endo or exothermic. It makes a difference here. So first off, it talks about, hey, if a reaction is endothermic, meaning heat is entering, so just as a reminder about that, that means our heat is a reactant. We can treat that endothermic, we can treat heat as a reactant. If our reaction is exothermic, that means heat is exiting, and we can treat heat as a product. The reason why that's important is because now we can use the same saying we did with concentrations and the fact that we shift away from what we add and towards what we remove to replace it. However, there's one key difference here than what we saw with concentrations. With concentrations, when I had all that shifting equilibrium, I changed Q from being what K is, and then I had to shift to get back to K. Here, I'm actually changing the value of K. So the shift is not to get us back to where we were originally, but rather the shift is to get to some new K, which is a big difference here, okay? So there's a chart here that kind of talks about the two different reactions here and how being endothermic versus exothermic and how changing heat would be different in the two scenarios. So let's first talk about the endothermic one. With the endothermic one, again, heat is entering, so we see it here as a reactant. So if I increase temperature, if I add heat in, remember we shift away from what we add. So shifting away from what you add would shift you to the product side. And if you're shifting, I'll put products. And if you're shifting to the products, that means products are increasing, reactants are decreasing. And so now my value of K will increase. On the flip side, okay, if I decrease the temperature, which would be done by removing heat, if I remove that heat, remember I shift towards what I removed to replace it. So that means I'd be shifting here to the reactant side. And shifting to the reactant side will cause the products to decrease, the reactants to increase, and so therefore my value of K would decrease overall. Okay. However, exothermic, now all of a sudden my heat is on the other side. And if my heat's on the other side, then the effects that we're going to see are going to be exactly the opposite. If I'm adding heat in, I shift away from what we add, so that would be shifting to the reactants. And shifting to the reactants would cause my value of K to decrease. And exothermic reaction would shift to the product side if I remove heat, because again, I shift towards what I remove to replace it. And so that would cause your value of K to increase. So again, the big difference here is that I'm shifting to a totally new value of K. I'm not just trying to shift things around to get back to K. So be very careful with the heat temperature ones. All right, there's two examples down here. If y'all want to try them out, you're more than welcome to. I actually want to talk about the chart on the next page because the chart on the next page is probably the most likely type of question you'd be asked either in a multiple choice question, or these columns that you see here would be what you would want to talk through, say on an FRQ question about Le Chatelier's principle. First thing we need is we need to get ourselves a balanced reaction. That's kind of the key thing here. And we also want to place heat. We notice this delta H of the reaction is a positive 68 kilojoules. And so if that has a positive with it, then that means that this process is endothermic. So that's going to make a difference where we put that heat. It says we have a synthesis reaction of nitrogen dioxide gas from nitrogen gas and oxygen gas. So that means I have N2 gas plus O2 gas. And I'm going to put an equilibrium double-sided arrow since it says it's an equilibrium synthesis. And that's going to have NO2 gas. To balance this, let's see here. We're going to need a 2 here and a 2 there. Also, because we said this is endothermic, I'm going to go ahead and place my heat on my reactant side. That heat is entering. You can either put the 68 kilojoules here or you can just write heat. Totally up to you how you want to write that. We just need to place heat as being a reactant or product. So again, these columns here are kind of your talking points if you were doing an FRQ question. So let's look at this first one here. This first one says, hey, we're going to add N2. If I add N2, then what that means is I am adding a reactant in here. And to go back to our lovely equation here, if I'm adding in a reactant, that means this denominator is going to get too big. And if that gets too big, then what that means is that my Q is going to decrease. And so what that means is that right now Q ends up smaller than K. And I need to do something in order to get Q back up to K. And so I'm going to need to shift some things around in order to do that. So to get Q bigger again, I would need to increase my product side. So I'm going to shift to the products. And in result of shifting to the products, what that ends up meaning is that my reactants are going to decrease. So we're going to see a decrease in reactants and an increase in products to reestablish our equilibrium. Now again, these are your talking points if you were doing an FRQ. What I would want to say is if I add nitrogen gas in, because that is a reactant, that would cause the Q value to decrease where it ends up being smaller than K. To increase the Q, I would want to then shift to the products in order to reestablish equilibrium, which means that reactants concentrations decrease and product concentrations increase. Those are the exact things that you would want to talk about. However, I will tell you this, if you're answering a multiple choice question and you want to do this a little faster, the fast way of doing this is to say, hey, if I'm adding N2, that means I'm shifting away from what I add, which means I'm shifting to the products. And they might just say, hey, am I shifting to products or reactants? And so then you have your answer. Or they might ask you like, hey, would products increase or decrease? Well, if I shift to products, then that means those are increasing. And you can see I answer that a lot faster than talking through all these points, okay? Let's do another one here. It says, hey, I'm going to remove some O2. Well, if I remove O2, that's removing a reactant. So now my reactants are going to get too small. My products are going to be bigger than that denominator. And so what that means is that my Q is going to end up too large. So Q right now is bigger than whatever my K value is. Again, neither of these situations are changing K. We're changing Q to be off of K, and we got to get everything shifted to get back to K. So in order to decrease Q to get it back to equal K, that means I'm going to have to shift to the reactants, which means the reactants are increasing and the products are decreasing. Okay, next one, it says, hey, I'm going to decrease the volume of reaction vessel. Well, if I decrease the volume, that means I'm making my container smaller. And unfortunately, that would increase the concentrations of both reactants and products. So I'm going to kind of have to think through this in a different way here. What I'm going to do is I'm going to think about the number of moles. So if I'm decreasing my volume, I would want to have less people at my party. So I would want to shift to the side that has less moles. And if I look back up here, I see the reactant side has a grand total of 3 moles of gas, whereas the product side only has 2 moles of gas. So that means I would want to shift here to the product side. And again, if you want to give yourself a note here, I'm shifting to the side that has less moles. That is the reason why I'm shifting to that side. Shifting to the products means that reactants decrease and products increase to get back to equilibrium. All right, next one says, hey, I'm going to heat the reaction vessel. If I'm heating the reaction vessel, that means I'm adding in this heat right here. Now, I'm going to warn you, this one you got to be careful on. I usually, when I see it's a temperature heat one, I use the little tricky saying that I'm going to shift away from what I add, meaning I'm shifting to the product side. I actually answered this first. If I'm shifting to the product side, then that means reactants are decreasing, products are increasing. Now, this didn't get us to where we now got to shift back to K. This has shifted K to a new value. So you got to be really careful on this one. And shifting K to that new value, what that means is that if products have increased, that means my K has now increased. Okay, which means that the Q and the K are equal. I'm not going to worry about that one, but that the K value is bigger than it was before. Okay, all right, this next one is kind of a trick. It says, hey, add xenon in. Do you see xenon up here? Nope. If we think about xenon, it's in group 18, which we know are the noble gases, which are inert. It's not going to react with anything in here. And so what that means is that this one is a trick. This one would cause no equilibrium shift. Let's see if I can spell equilibrium shift. No equilibrium shift. The only thing this would do is it would increase the total pressure in the container. That's all it would do. Okay. There is one other one on here that is a trick that we haven't talked about yet. And if you kind of look through these, you probably notice that it kind of stands out because we haven't talked about it, and that is the adding a catalyst. Now think back to what a catalyst did. A catalyst increases the speed of a reaction, right? Doesn't change the amounts of anything, just increases the speed. Basically what it does is it allows our seesaw to balance faster. So what that means is that this one is a trick question and it would cause no equilibrium shift. All that equilibriums does, or excuse me, all that the catalyst does, it allows us to reach equilibrium faster. So what that means is that if you do one of the other effects like increase, oxygen or decrease nitrogen or whatever, if you do one of those other things, what it'll do is it'll allow the seesaw to balance out more quickly. But it doesn't change where the seesaw is balanced at. So just kind of be careful on that one. All right, so here's what I want you to do. I want you to pause this video for a moment. And I want you to see if you can answer these other ones that are on here. Have you paused it yet? Pause the video. Pause it. See if you can answer them. And hold on. I'm going to find where I hid my key. Did you pause it? Here we go. I put the answers up. Are we ready? Ready to see answers? Okay. Here's the answers to the rest of those. So you can see if you were able to get them. Woohoo. Yay. And are we feeling this guy down here? Feeling a little stressed out? Yeah. I know it. I feel it too. All right. Hope this helps. Please feel free to email me or contact me if you have any questions. Bye, guys.